Graphs of cosecant, secant, tangent, and cotangent. Let's start by focusing on the graphs of cosecant and secant. So here we have y equals cosecant x, and so we see here's the graph. So the graph is these solid blue portions. They look like little u's that are right side up and upside down. And the way to understand why the cosecant graph looks like this is to remember that cosecant x is the reciprocal of the sine function. So cosecant x is 1 divided by sine x. And because we have a function of x in the denominator, if there are any values that make the denominator equal 0, that would be places where the graph is undefined. So here, the sine function is 0 at 0. So right at 0, the sine function is 0. So that means I can't divide by 0. So on the cosecant graph, there can't be any point that exists along that vertical line, which happens to be the y-axis. So there's actually an asymptote there. Now it's not really emphasized here because that's the y-axis, but there is a vertical asymptote along 0, 0. And if I plug pi into the sine function, sine of pi is equal to 0. So notice that right here at pi, there's another vertical asymptote because I can't divide by 0. So I can't plug pi into cosecant x because I'll get 1 over 0. So any place where the sine function is 0 is going to be a vertical asymptote on the cosecant graph. And from there, you can see this lighter colored graph here. That's actually the basic sine function. And so how is cosecant related to the basic sine function other than these asymptotes? Well, any x-intercept becomes a vertical asymptote, but the maximum values on the sine graph, right, so this peak point here, becomes a minimum value on these little U shapes. So here, the maximum is at 1. That's the highest the wave can go, right, the amplitude, and that's the lowest point on my cosecant U shape. And then when I have a minimum value, so -1 is the minimum, for my sine function, that becomes the maximum on the little u's of my cosecant function. And similarly, to graph secant x, we have to remember that secant is 1 over cosine x, that's its reciprocal. So for the same reason, anywhere the cosine function is equal to 0, or is on the x-axis, there will be a vertical asymptote along the graph of secant x. So here, this lighter colored graph, that's the graph of cosine. So that's not part of the graph of secant. It's just a guide to helping me draw the graph of secant. So here's just a quick sketch of the cosine function, which we should know. And any x-intercept of the cosine function, so pi over 2, 3 pi over 2, those are vertical asymptotes. And then same idea, it's a bunch of U shapes where the maximum value of cosine is the minimum value of secant, and the minimum value of cosine is the maximum value of secant. One last note, cosecant and secant are also periodic functions, so one complete period of, let's say, the secant function is one complete right side up U shape and one complete upside down U shape. So these two pieces together are one complete period. Here are the steps for graphing secant and cosecant. We're going to graph the corresponding reciprocal sine or cosine graphs, ignoring vertical translations. The x-intercepts on those sine or cosine graph that we just drew become the vertical asymptotes on the cosecant-secant graphs. And then the local maxes and mins of sine and cosine becomes the local mins and maxes of cosecant and secant. So just drawing those U shapes with the correct mins and maxes. Let's look at an example. We're going to graph one period of y equals 3/2 cosecant 4x. So the first step is to go ahead and graph the reciprocal function. So that's y equals 3/2 sine of 4x. So we're really going to get practice in graphing our sine and cosine functions here. So what we know about the sine function is the amplitude is 3 over 2. We know that the period is 2 pi over 4, which is pi over 2. The quarter period is 1/4 of the period, 1/4 of pi over 2, so that's pi over 8. And there's no reflection to this graph, and there's no phase shift, there's no vertical translation to worry about. So we'll just go ahead and start to label our axes. So we have 0, and the end of our period is going to be pi over 2, and we'll split it into 4 equal parts using 5 tick marks. And the tick marks are going to be pi over 8 apart. So we have 1 pi over 8, 2 pi over 8, 3 pi over 8, and then of course 4 pi over 8 is pi over 2. We can reduce this one down, pi over 4. And then we have our y-axis label, which is just going to be the amplitude value. So negative 3 over 2 and 3 over 2, right? So these are all the tick marks I need labeled to graph my sine function. But when I graph my sine function, I'm going to graph it as a dotted function because it's not the actual graph I'm looking for. So I'm going to go ahead and sketch my sine function here as a dotted function. And now we're going to go ahead and apply those steps to get us to a cosecant graph. So once you've graphed your corresponding sine function, that reciprocal function, any x-intercept on this graph, so here's an x-intercept here, here, and here, those are going to be the vertical asymptotes of my cosecant graph. So I'm going to go ahead and draw some dotted lines to represent the fact that they are asymptotes. So I've really not drawn any points at all so far on my cosecant graph. So everything here is just to help me draw my cosecant graph. So now I will finally start to sketch out one period of my cosecant graph. So the maximum point on the sine graph, which would be up here at pi over 8 3/2, is going to become the minimum point of my u. And my U shape has to approach these asymptotes. So I don't want to do something like draw it really skinny right here in the middle. So I want to go ahead and extend it out and make sure that I approach those asymptotes on both sides. And then the minimum on my sine graph down here at 3 pi over 8 negative 3 over 2 is the maximum of the other part of the period, that downward facing U shape. Right? So an upward facing U shape and a downward facing U shape is one full period of my cosecant graph. So the actual graph itself is these purple parts here. All the rest of this was a guide to just helping me sketch that graph. In this example, let's graph one period of 2 secant pi x over 2 plus 1. So we're going to start by graphing y equals 2 cosine of pi over 2. I'm going to leave the pi over 2 in front of the x. And I'm not going to graph the plus 1. I'm not going to address the vertical translation. So I'm just going to go ahead and work with 2 cosine pi over 2x. So let's go ahead and recognize the amplitude is 2. The period is 2 pi over 2. Well, that's 2 pi times the reciprocal 2 over pi. The pi's are going to cancel, so I have a period of just 4. And that's nice because then the quarter period is 1/4 of 4, which is just 1 after the 4's cancel. So my tick marks are just 1 unit apart. So normally we start at our 0, and I'm going to just go ahead and jump straight to labeling my equal tick marks 1, 2, 3, and 4, right? They're just nice whole numbers there, 1, 2, 3, 4. They don't have pi because we eliminated the pi when we multiplied by the reciprocal. And let's see, we have 2 as our amplitude. So I have, let's mark positive 2 and negative 2. And then we're going to go ahead and sketch the cosine function. So the cosine function starts up at the amplitude, and then it goes down to the x-axis, down to negative of the amplitude, back to the x-axis, back up to positive of the amplitude. Whoops, corrected it for me and I didn't want it to. Okay, there we go. So that's a quick sketch of the cosine function, but what we're really looking for here is we're looking for what are those x-intercepts so that we can go ahead and draw some vertical asymptotes. So I'm going to go ahead and sketch my vertical asymptotes now at 1 and 3 at those x-intercept locations. Alright, so from here I'm going to go ahead and start to sketch my secant graph, although I'm going to have to be careful about something, but we'll start to sketch my secant graph. It's just I haven't addressed the +1 part yet, but we'll just go ahead and do the secant part first, which is any maximum on the graph of cosine is going to be a minimum on the graph of secant. So here I'm going to have a portion of the graph that upward facing u. Now I know the other side though would continue on, and I actually know as well that there's going to be a vertical asymptote on the other side at the specific value at -1. So I can go ahead and just keep going with the original cosine function and find more vertical asymptotes. So that's one complete u, and then I also have another one, right? That's going to be my other u, and then I can also do this part over here, right? That upward facing u shape, half of it, right? So if I wanted to see the complete right side up u and upside down u, I could have just left this side and this side, and then this bottom part here. That would still be one period, but we often just like to see a full right side up u and an upside down u. But so far, this graph right here is the graph of 2 secant pi x over 2. So what I want to go ahead and do finally is shift everything up 1 on the last piece with the u shapes. So let's go ahead and wrap up the graph by doing that. So that means it's going to be up at 0, 3. And I'm going to go ahead and complete my u, still sticking within those asymptotes. And then this u shape here was at 2, -2, so now it's going to be at 2, -1. And it's still trapped between those asymptotes. So if there's a vertical translation, we just handle it absolutely last. We graph the cosine function without addressing it at all. Sketch that graph of secant even without it, and then move everything up. Because we don't want to affect the location of those vertical asymptotes by drawing the graph of 2 cosine pi over 2x plus 1. That's going to affect the location of those asymptotes. Now let's look at the graphs of tangent and cotangent. So first we'll focus on the graph of tangent x. So let's just take a look at it. Here's the graph of tangent x. Definitely has a completely different shape from the sine and cosine functions and even the secant and cosecant functions. But what it does have in common with the secant and cosecant functions is that it has asymptotes. Now the reason that it has asymptotes is because, if you recall, tangent x by the quotient identity can be rewritten as sine x divided by cosine x. So anywhere the cosine x function is equal to 0, it's going to give me a vertical asymptote location. So if we remember, the cosine function goes at pi over 2, has an output of 0, so it goes through pi over 2, 0, goes through 3 pi over 2, 0. So that's why those are locations of vertical asymptotes. And so it has this general shape here. I like to remember it by thinking that it looks like the x cubed graph. So tangent x looks like a bunch of repeated copies of x cubed. Something else to go ahead and notice is that it passes through the origin, the tangent graph, and the values on all of our trig functions really come from what happens when you substitute in different values into our trigonometric function. So, tangent of 0 is 0, so that's the coordinate point 0, 0. Another value that we often plug into the tangent graph is pi over 4, which is halfway between 0 and pi over 2. So if you'll notice here, pi over 4, if you substitute pi over 4 into tangent, what comes out is 1, right? The value 1 comes out. So with symmetry here, I can see that if I plug in negative pi over 4, negative 1 comes out. And then I'm approaching these asymptotes here, so there's those remaining points on the graph that again makes it look like a bunch of repeated copies of x cubed. And then the cotangent graph does look sort of similar to the tangent graph. It too has asymptotes. There is a vertical asymptote, although it isn't very clearly seen here because it's on top of the y-axis, but there is a vertical asymptote along the y-axis, and any place where the sine function is equal to 0. So pi, 2 pi, negative pi, those are all vertical asymptote locations. And the shape looks similar to tangent, but it's reflected over the x-axis. So now this curve sort of changes directions. So a lot of tangent and cotangent is memorizing just that general shape and then understanding where the asymptotes would be based on, rewriting tangent as sine over cosine, cotangent as cosine over sine. One other thing to notice that's different is the period is no longer 2 pi, like a standard sine or cosine graph, or even secant or cosecant. The period is actually pi. So one of these curves here happens in a length, or in an interval length of pi. So here, this interval length, if I go pi over 2 to the right and pi over 2 to the left, that's a total period measurement of pi instead of 2 pi. Let's talk about steps for graphing tangent and cotangent. So let's say we're given something like a tangent bx plus d or a cotangent bx plus d. As I said, a lot of it is memorizing, so we have to make sure to memorize the basic graph of tangent and cotangent, that shape, the fact that tangent goes through the origin, kind of looks like x cubed. Cotangent has a vertical asymptote along the y-axis and has that flipped shape. And from there, we know the period of the graph is pi over b instead of 2 pi over b. So the period formula is slightly different for tangent and cotangent. It's pi over b, not 2 pi over b. The number that's in front, we don't call it an amplitude. We also don't call it an amplitude for cosecant or secant. We just consider it a vertical stretch or compression, that number that's multiplied in the front. And d is still a vertical translation. A number on the outside that's added or subtracted shifts me up or down. And again, this value could be added or subtracted in the front or in the back. Alright, in this example, we want to graph two periods of y equals 2 tangent x plus 1. Alright, so the main function here that we're working with is the tangent function. So what I kind of like to do is just start by drawing the general shape of the tangent graph on my xy plane. Now at the very end we'll handle our shifts, so this isn't going to be the actual final answer, but I am just going to go ahead and draw a regular old tangent graph shape. So looks like, again, an x cubed. I know it passes through the origin, and I know that it has asymptotes, so I'm also just going to go ahead and sketch some asymptotes. Now at the very end we'll go ahead and shift everything up, but for now I just want to graph just one. Would be one period of a generic tangent graph. Passes through the origin, has some vertical asymptotes. This is its general shape. And now it's a matter of labels, really. At this point it's just a matter of labels, and then we'll address the shift. So let's go ahead and talk about what those labels are going to look like. So let's start by talking about the period, since that is a different formula. The period is pi over b. The value of b is the number in front of x, and that's just 1. So the period, the period is just pi. And we still want to think about the idea of quarter periods here. So 1/4 of pi, well, that's just pi over 4. So the tick marks are going to be labeled pi over 4 units apart. So we have our 0, 0 as one of the values, and then I have a tick mark halfway here, and that's pi over 4, and then this asymptote is at pi over 2. And then here we have negative pi over 4, and this other asymptote is negative pi over 2. Now, since I do want two periods, let's keep going with this. So we're going to have 1, 2, 3, 4 more here. So we have 1 pi over 4, 2 pi over 4. This tick mark would be 3 pi over 4. This would be 4 pi over 4, which is just pi. This would be 5 pi over 4, 4. And then this would be 6 pi over 4, which is 3 pi over 2. And so that would be our next asymptote location. I missed a little bit, that's okay. And so we'd have another tangent curve going on. Man, my drawings are not great right now. All right, we'd have another tangent graph going on here. So we have the x-axis labeled. So now we just need to go ahead and label the y-axis. So the 2 in the front we think of as that vertical stretch or shrink. So it's going to be a vertical stretch by a factor of 2. But what's nice is that if we remember on a tangent graph that this point here, this halfway point, passed through pi over 4, 1 originally, right, passed through pi over 4, 1. Now, because of the vertical stretch by 2, it's going to pass through pi over 4, 2. So the halfway point is up here at pi over 4, 2, and then down here at negative pi over 4, kind of missed, didn't it? Let's see if I can erase that and make it go through there nicely. So we'll have it go through here and here. All right, so negative pi over 4, negative 2. And the same thing applies over here. So this would be 5 pi over 4, 2. And then negative 3 pi over 4, negative 2. I'm going to make it a big circle to fudge it a little bit and make it work. So right now, this is the graph of 2 tangent x. So we have our x-axis values labeled, and now these y-axis values labeled. The last thing to do is shift everything up 1, and then that'll finally be our graph. So switching colors here, I'm going to need an extra tick mark up here since I'm moving everything up 1 unit. So it would be pi over 4, 3. And then instead of 0, 0, it's going to be 0, 1. And instead of negative pi over 4, negative 2, it's negative pi over 4, negative 1. And then I'm still trapped between these vertical asymptotes, so I'll just go ahead and extend them a little bit. And then connect this with a general shape. So that's 1 period, and then do the same thing here. Move this up 1 unit, move this up 1 unit, move this up 1 unit, and then connect them together, making sure to approach these asymptotes, so extend as necessary. So this green graph now is 2 periods of 2 tangent x plus 1. Now let's go ahead and graph 2 periods of y equals negative 1/3 cotangent 2x. So I'm going to go ahead and start by, again, just recognizing this is a cotangent function and just sketching a general cotangent function without any labels. So just a general cotangent function, I have to remember, has a vertical asymptote along the y-axis. And then I'll go ahead and put another vertical asymptote over here. And I'm drawing 2 periods, so I'll put another vertical asymptote over here. And then the general shape of cotangent, it's a lot like tangent, except that the shape is flipped over the x-axis, right? So I'm just focusing on a generic cotangent graph for now. So it's going to look something like this. And I'll put another one over here. These are supposed to go halfway. And so I'm going to go ahead and leave my graph like this. So again, now it's just going to be a matter of labels, and then we are going to have to address this negative, which is going to reflect the graph. So this right here, what I've sketched, is just generic copies of like repeated cotangent graphs. So now let's start to label things. So we have our period, and the formula for the period is pi over b. The value of b here is 2, so the period is pi over 2. The quarter period is 1/4 of that. 1/4 of pi over 2 is pi over 8. So let's start to label. So we have 0. We have to label 4 equal parts, right, with 5 tick marks. So we have pi over 8. 2 pi over 8 is pi over 4. 3 pi over 8. 4 pi over 8 is pi over 2. And then this direction, those would all just be negative. negative pi over 4, negative 3 pi over 8, negative pi over 2. So my x-axis is labeled. And then the y-axis, the vertical compression, right? So 1/3 is less than 1. We're going to have a vertical compression by 1/3. Well, here I haven't labeled anything yet, so I'm just going to go ahead and sort of cleverly label things here. I know that the y value has to be 1/3 at the halfway point here between 0 and pi over 4. At pi over 8, that y value there would have to be 1/3. So this right here is going to be 1/3, and then down here 3 pi over 8 is going to have to correspond to negative 1/3. Same thing here, same thing here. So that's where that vertical compression, or that number in front, is going to come into play. It's going to be how we label the y-axis. So what I've sketched here, these two dotted cotangent graphs, they are 1/3 cotangent 2x. But I want to graph negative 1/3 cotangent 2x. So I'm going to have to reflect these over the x-axis. So I'm going to go ahead and do that finally. Let's go ahead and switch colors here. So negative pi over 4, 0 will stay the same, but now I have negative pi over 8, 1/3, negative 3 pi over 8, negative 1/3. It's going to look like this. And then we'll label those flipped points over here. So now this green graph right here, this is the graph of negative 1/3 cotangent 2x. And so sometimes, it can get a little bit confusing, like which graph am I looking at based on like the shape. So this is, it looks like a tangent graph because the general shape looks like an x cubed graph, but it's all about where the asymptotes are, right? So because there was a vertical asymptote along the y-axis, that's why I would think cotangent graph. Now, there is a way to rewrite this as a tangent graph if we start talking about phase shifts, right? Like shifting left or right. But the easiest thing here would be to identify this as a cotangent graph because of where the asymptotes are located, right? We have to remember the tangent graph passes through the origin. Cotangent graphs have a vertical asymptote along the y-axis. So even though the shape looks like a tangent graph shape because of the reflection, we do want to associate this with the cotangent graph instead. I just want to quickly make sure and add this did reflect the x-axis, so we want to make sure and include that in our description.